scrap paper and philosophy, and let's jump right into the stationary hypothesis, which we did last time. That is to say, the electromagnetic wave is a spinning magnet, and what's actually perfectly stationary would be like the center of the magnet right there with respect to the vacuum. So let's look at that. Here we see the field lines. They go away from the north and towards the south, but we're not going to worry about any of that. This is the picture that we're actually going to look at. You see, the field lines are really, really thick near the North Pole. We see the field lines are really, really thick about the South Pole. We see this picture is reasonably symmetric. It was made by an actual experiment by throwing iron fillings to create the pattern. So here we see that there's not many field lines there. And around here you can see as we go, I don't know if this picture is centered, but I actually, yeah, it's, you see this is not symmetric. There's more field lines here, but you know, it's a lot of happenstance from the way you throw the iron fillings at the magnet. So the happenstance says that these field lines are going to be really weak here, and they're going to be really strong here and really strong here. And that's the picture we're going to use. So we begin, where do we begin? Well, let's begin here. Well, actually, let's look at the electromagnetic spectrum first. So, EM spectrum. Let's look at this one. So, we're going to look at what hopefully is an actual electromagnetic wave called an ELF. It has extremely low frequency. It's spinning at 3 hertz, and it's got a wavelength of 100 million meters. So this thing is huge. And we're going to follow this wave for 1/3 of a second, because 1/3 of a second is a full cycle. Now, we're going to assume we're right here. And remember, the stationary hypothesis, the superluminal principle says that mass is not stationary. So when we say that we are here, what we really mean is that our mass subsystems are traveling really fast, but our mass subsystems are moving in Brownian motion really fast. So our mass system as a whole can stay reasonably fixed in space around this point. Now, let's locate the distance of 100 million meters, because the distance of 100 million meters is not the distance from the North Pole to the South Pole. Here, for simplicity, I only labeled the North and the South Pole plus and minus. It doesn't matter which is which. Remember, because of the symmetry in the picture, we don't really care which is which. We know the field lines are around the plus sign. We know the field lines are around the minus sign. We know the field lines tend to disappear around here and around there, and that's enough. So, but we do want to locate this distance, right? 100 million meters. Well, 100 million meters would be the circumference of this entire circle, and the distance between the North and the South Pole right there, this diameter, would actually be 100 million over pi. Okay, so we are here, and what we want to do is imagine that this is spinning, and that we are measuring the electric and magnetic fields. And we want to see what kind of picture we measure. Well, what kind of graph we create. So I'm going to start doing it right here. We have t equals 0, t equals 1/12, and then on the next cycle we go to 1/6. On the next cycle we go to 1/4. And then when we reach 1/3 of a second, we're done with a full cycle. We have a perfectly symmetric situation where we've gone full circle and we're back to this picture over here. Now, on this picture over here, we are going to start right there. And what we're going to observe is that, if anything, the field, the horizontal component from this plus sign is canceling out the horizontal component from this minus sign. We're only left with a vertical component for the magnetic field, right? Right there, a vertical component of magnetic field. And because we happen to know that this is our best guess for a small field, right? Because when the magnet goes here, we're going to have all these field lines. So we're gonna put a 0 right there for the magnetic field. Now, if you want to assume that this is actually a small positive number instead of 0 for the magnetic field, you can, because we're going to transition anyway all the way from the maximum to the minimum. At some point, we have to cross 0, because that's the if these are continuous quantities, that's the a theorem. If these are not continuous quantities, if these are discrete quantities, well, then you can have a tunnel from positive magnetic fields to negative magnetic field without ever crossing 0. Well, so where were we? We were right here. We were observing this. We said the magnetic field is 0. Next, we're going to be at this drawing here. And at this second drawing, what we're going to observe is that one of the tips of the magnet, very, very rich in fields, is going to be right more or less where we are. And as soon as that flies away from us, we're going to lose a lot of field lines. Well, for one thing, the reason why I'm saying this is that at this point, the magnetic flux is very big. You see, at this point, the magnetic flux is the change in field lines. So, you see, at this point, the magnetic flux is very small because the positive is approaching us, but the negative is moving farther away. Wait a second. Here, the positive is approaching us, so we're gaining flux from the positive, and the negative is compounding this effect by moving away, you see? So here, the flux, the change in the field lines is actually very big. And the way we interpret that is that the electric field is going to be at a maximum, because what is induced by the magnetic flux is the electric field. Okay, that's it. Let's move on to the second picture. Well, on the second picture, obviously the magnetic field is at a maximum. Okay, so let's write that right in. Here's the B field on time. Here's the maximum. And then we go to t equal 1/6. Again, we have a symmetric situation here to t equals 0. So we're going to call that a 0, even though we know there could be a tunneling effect from positive small quantity to negative small quantity. Excuse me. Okay. Maybe I should answer that, I don't know. Okay, let me start over again. So, let's start at this first drawing here. We have we don't have a lot of magnetic field, right? We know that we don't have a lot of magnetic field. Look, where's the magnet? That's going to be helpful. So we're around here. We know that we don't have a lot of magnetic field. But we also know that this is approaching us while this is moving away. We're also going to know that we're going to drift towards, well, where are we going to drift towards? We're going to drift towards here, towards the South Pole, or towards the North Pole. Either way, this is symmetric. The wave could, the magnet could be spinning either way, clockwise or counterclockwise. So we're going to go from zero fields to lots of fields, very, very quickly. We're going to write that in right here as moving from a zero magnetic field to a maximum magnetic field. By the way, the electric field is coming in and out of the page, right-hand rule. I didn't draw the magnetic field. I'll eventually write down the electric field. Well, as we move from 90 degrees to the second picture over here, we have the North Pole right on top of us. So this is where we are. And we see that although the magnetic field is at a maximum, there's not going to be a lot of change, because here in this picture we had a plus approaching us and a minus moving farther away. They tend to reinforce each other. Here we have a plus sign that's barely moving with respect to us, and a minus sign that's barely moving with respect to us as far as the field lines go. So here, the magnetic flux is going to be very low, but the magnetic field is going to be very high. So this is t equals 1/12 seconds. Let me draw that in. Where's the field? Okay, let me use this drawing. So on this second picture, it goes first picture, top left, second picture, top right, third picture, bottom left, fourth picture, bottom right. So on this second picture, we have a maximum E field, electric field. No, I'm sorry. The first picture we had a maximum E field. At the second picture, the fields aren't the flux lines aren't changing very much, so we have no flux. See, here we have max flux at the beginning. First picture, second picture, we have no flux, so we have a zero electric field. Or close to zero. Then there's the third picture, where we're back to the situation of the first picture, and here we have no magnetic flux, close to zero. No magnetic field, close to zero. We do have magnetic flux. We have lots of magnetic flux, because here the minus sign is approaching us, and that's adding to the fact that the plus sign is moving farther away. So that's a lot of flux. Or we can look at that picture of the actual magnet with the iron fillings and remind ourselves that of where we are going in a circle around that magnet. And this is the picture that we're going to end up with, okay? We're going to go from t equals 0 to t equal 1/3 seconds. The magnetic field's going to go sort of like this, remembering that we're not sure about this zero here. You know, some people say that only positive stuff exists in the universe. there's no such thing as zero, and there's no such thing as negative numbers. The only thing that exists in the universe is positive amounts of stuff. So we're not doing continuity exactly. If we were doing continuity, we could use the intermediate value theorem to say that this crosses the axis at zero. I guess we're not. But the point is that the electric field and the magnetic fields are going to sort of work out to what we would expect if we were measuring an electromagnetic wave. And sometimes using radio antennas, we do measure electromagnetic waves, except they are not, we don't measure them, we capture them for their information. We destroy them. Except we're using electromagnetic waves that have dimensions of like about a meter, because that's close to the dimension of our antenna. And so the antenna can very effectively interact with this object, right? Remembering, of course, that the antenna is not at rest. That's the luminocentric principle. And what's that? We are not. The antenna is not at rest. The spinning magnet is at rest. But that spinning magnet is going to be captured by the antenna. And the antenna is going to measure a reading. And I think that reading is going to pass our smell test for what this spinning magnet looks like and what we can say about these waves, this B field and this E field. Of course, if we really want to visualize this more carefully, we would have to imagine the electric field going out of the page and into the page as this thing spins on the two-dimensional page. And it's a tough picture, because we don't know if our imagination is being true to measurements. But we do know that this is reasonably true to measurements about what the electromagnetic wave will measure. And we know that in our model, the distance between time equals 0 and the distance between time equals 1/3 is that's one cycle. No, that's one full wavelength, right? That's a full wavelength. So the full wavelength is going to be the circumference of this circle. The what else can we say? Well, we can say what the dimensions of the magnet are from plus to minus. It's going to be just, that full circle divided by pi. And that's the wavelength divided by pi. And we can, well, I think my brain just stopped. Okay, so I'll leave you with that thought. Thanks for watching. Hello. So after I recorded this, I realized that it was way more complicated than I thought. Right here on this picture, if we're really going to claim that the magnetic field goes all the way down to 0, remember, we're right here. In this picture, we would be like right here. So this picture makes it plausible that the magnetic field really goes down to 0. But what we are really measuring is the perpendicular component of the magnetic field. Because if we were measuring the tangential component of the magnetic field, it wouldn't be 0, you would still, a compass or like a magnetic, whatever, ferromagnetic material would still want to go like that. Well, depends who's eating the fields, or like that. So it would be weak, but it wouldn't be zero. And especially the tangential component. The tangential component would not be zero. The perpendicular component would be zero. And as long as we're only measuring the perpendicular component, well, then what happens when we're right here? Well, if we're measuring the tangential component, there's going to be severe flux pretty soon. But if we're measuring the perpendicular component, well, we're going from, see, this doesn't really pass. This is a very nice representation, but it doesn't really help us as far as imagining everything that's going on here. I mean, we know that the magnetic field completely changes signs. So well, I don't know what's going on here. We know that the magnetic field completely changes signs, and what's that going to do in the picture? It's going to create the magnetic field wave. Even if we're stationary, if we're stationary right here, we know that the magnetic field is going to be a maximum or a minimum, whichever you choose. It's symmetric. And that's going to have completely flipped by the time this magnet spins 180 degrees. So there's not going to be a continuous, I mean, it's not necessarily going to cross zero. And that's going to be a problem because we're going to have to think more carefully about what sort of electric fields are induced or not. So, very nice hypothesis, but I don't know, maybe kind of iffy. I have to apologize for all this going back and forth, and now I will be able to wrap up this video. Because first thing, I'm going to emphasize that we've been considering the spinning magnet as a two-dimensional structure spinning on the same plane as this paper, but I haven't emphasized the speed c yet. The speed c is the speed at which it is spinning, and if you increase the size of this magnet or you shrink it, what is going to be conserved is the speed c relative to this circumference. So, by doing that, we can start to imagine the magnet as a three-dimensional structure, but we complete the third dimension by filling in the electric fields instead of filling in the magnetic fields. How are we going to do that? Well, first we're going to say there's a tangential component to the magnetic field, right there, this tangent. If we measure the magnetic field along the tangent to the circle, we're going to call that the tangential component of the magnetic field. If we measure the magnetic field along the perpendicular to the circle, we're going to call that the perpendicular component of the magnetic field. we're going to say that the entire tangential component is working on spinning the magnet at speed c. No matter how small or how large the magnet is, it wants to chase its tail. It wants to do that at speed c. And it's going to do that by using the tangential component of the magnetic field. Now, the perpendicular component of the magnetic field is what's actually going to fluctuate from the maximum to the minimum in our graphs and cross zero using the intermediate value theorem. That's the component that's going to do it. And we complete, in our imagination, we're trying to imagine a three-dimensional structure here. So we complete it by, well, first noticing that on the poles, there's going to be a low electric field in the polar regions of the magnet. So any electric field, we don't expect the electric field to appear here, and we don't expect the electric field to appear here. We do expect the electric field to appear here, and we do expect the electric field to appear here. And so we kind of imagine it going into the page here. It could be out of the page or into the page, you know. But once we choose that this one is going into the page, well, then we have to sort of imagine it going out of the page there. And I hope this makes the stationary hypothesis as plausible as it seems to me, because to me it seems so plausible. I don't want to let it go. Thank you. Thanks for watching.